This week is about limits of computation. Okay, so what we have done so far, we have formally defined our computational model using the Turing machine model. And now we want to understand the limits of the Turing machine model, limits of computation, which will then also lead us to understand actually limits of human reasoning itself. So in picture, what we have is we have the set of regular languages decidable, solvable by DFAs. We have the set of Turing machine decidable languages that encapsulates, of course, the set of regular languages. And then outside, encapsulating everything, we have the set of all languages. And we want to understand, well, is there something beyond Turing machine decidable? Can Turing machine solve every problem we have or not? Now notice that these are, of course, regular languages, Turing machine decidable, all languages. These are infinite sets, right? And the basic question we're interested in here is, given a set, is there an element outside of that set or not? And this is like one of the most basic fundamental questions that you can ask, right? So many questions of interest can be boiled down to the question of, oh, I have a set. Is there another element that's outside this set? And in this case, we have this kind of a question for infinite sets. So we need the right tools in some sense to reason about infinite sets. And this brings us now to Cantor, right? And his work on understanding the finite versus the infinite, trying to understand the landscape of infinite sets is going to be absolutely crucial, fundamental in our study of computation. And we'll see that his work basically directly leads us to talk about the limits of computation. We'll see that the main source for the limits of computation is basically the fact that computation, a Turing machine, an algorithm, is a finite object. Okay, it's a finite process. It takes finite length strings as input. The device that we're defining here is finite. All of these are, of course, very reasonable restrictions, assumptions to make when you're defining your computational model. And it turns out that's the source of really the limits of computation, and we'll see that. And then from there, we will be able to also talk about limits of human reasoning. And this connection also will not be too difficult to argue because human reasoning is computation. So we will be able to go from limits of computation to limits of human reasoning. So this basically describes the next 3 lectures, okay? Today's lecture is focused on basically Cantor's work. Next lecture more so on limits of computation. And then the lecture after that, next week on Tuesday, we're going to be talking about Gödel's work. These 3 gentlemen, kind of like my intellectual heroes, 3 of my intellectual heroes, and these will be like the most important, basically, some of the most important work they have done. And yeah, these are like some of the most important mathematical, scientific results in history, I would say. So should be a fun sequence of 3 lectures. Okay, so we will see, and you know, one thing I'll say is that hopefully you'll also be able to see that Cantor's work is actually very fundamental here. And from my perspective, pretty much Turing's work on limits of computation, Gödel's work, these are sort of like corollaries in some sense of Cantor's work. That's the way I view it, and perhaps you'll share that view as well after these lectures. Okay, so this brings us to the finite versus the infinite, right? So this is the first lecture, and this is what we try to understand now. And infinity in mathematics, let's talk about that first. Pre-Cantor, post-Cantor, what's the difference? Now, infinity is a very tricky concept, right? It has always been a tricky concept from the perspective of mathematics and human reasoning. Infinity is where, in some sense, our intuitions start to break down, okay? So we're finite creatures with finite resources. Our environment is finite. We can reason about finite things. We can judge the truth about finite statements. But when you talk about now infinite things and, you know, statements about infinite objects, you know, there are certain statements that we cannot really tell, you know, can this be true or not? We cannot even judge the truth of certain statements. And he's a famous mathematician, Gauss, like one of the most important mathematicians in history. He has a quote that sort of, summarizes the thinking of that time very well. He said, infinity is nothing more than a figure of speech which helps us talk about limits. And of course, Gauss, had important results using limits. So he's like, yeah, if you want to talk about limits, approaching some quantity, step by step, that's fine as a concept. But the notion of completed infinity doesn't belong in mathematics. So he's saying, now if you want to discuss infinite sets, define an infinite set, and reason about infinite sets as if they're just finite sets, it's that's not okay. Okay, the concept of infinite set, you cannot treat it like the concept of a finite set. And then Cantor comes along and says, look, this is wrong. Treat infinite sets as first-class citizens in mathematics. Okay? Don't discriminate against infinite sets, and we should be able to reason about infinite sets just like we reason about finite sets. And this is extremely influential. Cantor is considered to be the father of set theory because of his work on infinite sets. It's not like before that, people didn't think about sets, they thought about finite sets. But with infinite sets, then you get interesting stuff, and that's why he's considered to be the father of set theory, and set theory is at the foundation of mathematics, as you know. His work has been very influential also with respect to really accelerating the effort to formalize mathematics, because as I'll show you in the next slides, people had huge disagreements about Cantor's work, and then that accelerated the need to actually formalize mathematical reasoning itself. Okay, so so this is a very important work. But okay, so what were people's reactions to Cantor's work? So here's a reaction at the time. This is from a very important mathematician, Poincaré. He said, most of the ideas of Cantorian set theory should be banished from mathematics once and for all. Kronecker, another very famous mathematician. I don't know what predominates in Cantor's theory, philosophy, or theology. Scientific charlatan, corrupter of youth. Okay, so people were pretty mean to him. Wittgenstein, also a very famous logician, philosopher. He said wrong, utter nonsense, laughable. So people openly mocked him. Okay, but on the other hand, and by the way, I don't know if you know this, but Cantor spent a significant portion of his life in a mental health institution because, he had mental health problems. Maybe one reason is if you think about infinity so much, you go crazy a little bit. But also people think that, the fact that other mathematicians were so mean to him, that might have actually contributed to this as well. On the other hand, he had a very strong endorsement, okay? And you can't ask, in some sense, for a better endorsement than this. David Hilbert, the man himself, said, no one should expel us from the paradise that Cantor has created. And Hilbert, at the time, was a top mathematician. So this is a very strong endorsement. But, Wittgenstein doesn't care. He said, if one person can see it as a paradise, why should not another see it as a joke? So I bring all this up to say that, look, the top mathematicians at the time had huge disagreements about how to treat, how to understand Cantor's work. Some people just simply did not accept it. And so if you yourself, when you're learning about these topics, you kind of find it challenging or hard to wrap your mind around it, that's completely fine. Look, the best mathematicians didn't agree and found it hard as well. Okay? Now, Cantor was not the first person to really seriously think about infinity. There's another person. So who knows who this is? And actually, I might say, where is this picture taken from? Where is it from? Carnegie Museum of Arts. And who is this gentleman? Galileo, right? So this is Galileo. Galileo, of course, as you know, is a very important scientist. He had a lot of interesting results on physics and so on, but it wasn't just physics that he was interested in. He had other thoughts. And whenever he wanted to present his ideas in written form, the way he did it is not just like he wrote, oh, here's what I think and here are the conclusions. He kind of packaged this, his ideas, as a conversation between 2-3 characters and a discussion among them. Okay, so he had the following three characters. He had Salviati, this is the smart character, obvious Galileo stand-in, named after one of Galileo's friends. There's Segredo, intelligent layperson, he's neutral, named after one of Galileo's friends. And Simplicio, kind of the idiot, modeled after two of Galileo's enemies. So then, he had some thoughts about infinity, Galileo. So he had this following conversation between Salviati and Simplicio. So Salviati says, Galileo says, I take it for granted that you know which of the numbers are squares and which are not. And Simplicio is like, yeah, I'm quite aware that a squared number is one which results from the multiplication of another number by itself. Thus, 4, 9, etc. are squared numbers which come from multiplying 2, 3 by themselves. So they agree on this set. There's this set of square numbers. Good. Then Salviati continues, very well, if I assert that all numbers, including both squares and non-squares, are more than the squares alone, I shall speak the truth, shall I not? So basically he's saying, look, if we look at the natural numbers, all these numbers, 0, 1, 2, 3, 4, such so on, we can conclude this is a bigger set. There are more natural numbers than squares, of course. So most certainly, Simplicio agrees. Then he continues, if I should ask further how many squares there are, one might reply truly that there are as many as the corresponding number of square roots, since every square has its own square root, and every square has its own square. Right? So if we define the set of square roots now, right, every square really comes from a square root, and from every square you can get a square. So you have a one-to-one correspondence here between the square roots and the squares. Right, so we can maybe write this, right? The size of S is equal to the size of the square roots. Precisely so, says Simplicio. And then, but if I inquire how many square roots there are, it cannot be denied that there are as many as the numbers because every number is the square root of some square. So just making the simple observation that the square roots, this is just a set of natural numbers, right? So we can write the square root is equal to the natural numbers. This being granted, we must say that there are as many squares as there are numbers because they are just as numerous as their square roots, and all the numbers are square roots. So it's just saying, well, since we did square root equals n, and then s equals s square roots, well, then the size of s is equal to the size of n. Okay, yet at the outset we said that there are many more numbers than squares, but we said, the size of s is less than the size of n. So now he's observing a conflict here. Okay, so there's a conflict. So how do you resolve this conflict? And at this point, Segredo comes in. What then must one conclude under these circumstances? Well, okay, so let's bring in Cantor now and imagine what his reaction might be at this point. So Salviati continues. Well, we should say neither is the number of squares less than the totality of the numbers. So we shouldn't say this, he says. This is no good. And Cantor would be like, good, good. And nor the latter greater than the former. So we should also say that S is greater than N. So Cantor agrees, good, good. And finally, the attributes equal, greater, and less are not applicable to infinite, but only to finite quantities. And I think Cantor here would say, oh, so close, Galileo, you were almost there. Why not say that they're indeed equal? Why not resolve this conflict in the favor of the second bullet point right here? That was Cantor's idea. The reason I bring this up is because I would say, Salviati, or like Galileo, was not comfortable resolving this conflict. And I think that's a reasonable philosophical position to take. And if that's your position, and you're like Galileo and say, look, notions of equality, less than or equal, they're not applicable for infinite sets, that's completely fine. You can take that position. What I want to highlight, underline here in this lecture, is that you can accept all of Cantor's work having Galileo's position. Okay? You don't have to necessarily think about less than or equal to, but you still accept and use Cantor's work, and we'll see that. Okay? Now, there are two great ideas coming from Cantor. The first one is that we can use injections, surjections, bijections to compare sets. And the second amazing idea is the diagonalization proof technique. The diagonalization proof technique is one of the most important, maybe I would say top 5 proof techniques in all of mathematics. Okay, it's relatively simple and super powerful proof technique, and we'll go over that. But let's start with great idea number 1. Now, I assume that you have seen this stuff before in concept, so I'm going to go pretty quickly, relatively quickly on this stuff. But feel free to stop me if something is not clear. Okay. Now we're going to do this in 2 parts. First, I want to talk about like finite sets. Let's talk about finite sets, and then see how these things generalize to infinite sets. Okay, so comparing size of finite sets. If you have 2 finite sets like this, x and y, x has apple, orange, banana, melon, and y has 200, 300, 400, 500, and you want to say, oh, the size of x is equal to size of y. What do you mean by that? Well, what you mean by this is, well, I can basically put one-to-one correspondence with the elements of x with 1, 2, 3, 4, right? So that's sort of like you're counting the elements of x. And then you count also the elements of y, and you say, well, both sets have size 4, so this cardinality of x is 4, cardinality of y is 4, so therefore they have equal size. The insight of Cantor is that, hey, you can remove the middleman here. You don't need the middleman. You can just say, look, these sets are equal in size if there's a bijection between them, if there's a one-to-one correspondence between x and y. Okay, and actually Cantor was the person who introduced the concept of one-to-one correspondence. Okay, so this is pretty intuitive. And what about, let's say x, the size of x is less or equal to size of y. Now I removed one element from x, so it has 3 elements. Well, once again, you can sort of count the number of elements here, 1, 2, 3. Y has 1, 2, 3, 4, and therefore it's bigger. But, again, you can actually remove the middleman here and say, look, we're going to say the size of x is less or equal to size of y if there's an injection from x to y, right? So you're able to do this kind of define this injective map from x to y. And of course, from prereq course, like, if there's an injection from x to y, there's also a surjection from y to x. So we can reverse these arrows. And 400 didn't have anything, but we can arbitrarily map it back to some element, doesn't matter. And now you have a surjection from y to x, and it's the same meaning. The size of x is less or equal to the size of y. Okay, so there are 3 important types of functions, and this is just a reminder for you. I'm not going to spend time explaining these things in detail, given that you've already seen this. But injective functions, surjective functions, and bijections. These are important 3 types of functions. Injective, right? It's like if you have an injection from x to y, basically that means that no 2 elements of x get mapped to the same element in y. Right? So in picture, we have this kind of a situation. Right? 2 elements don't get mapped to the same element y. I guess mentioned this before, but the way I like to think about injections is kind of a labeling mechanism, right? So if you have an injection from x to y, you're basically saying for each element of x, there's a unique element of y, which you can think of as the label for that element x. Okay, so here's the notation that maybe you have not seen before. So if there exists some injection from x to y, I'm going to use this notation with the hook arrow. Okay, all this is saying, this notation does not specify what the injective function is. All it says is that there exists some injection from x to y. Now you know what a surjective function is, right? So this is a function in which all the elements of y get covered. Good. So in this case, I'm going to use a double-headed arrow. And bijective, well, it's bijective if it's injective and surjective. Right? In this case, we have a one-to-one correspondence between the elements of x and the elements of y, and this is the notation I'm going to be using to left-right arrow. Okay? And as we've discussed, right, we're going to think about these as, x is less than or equal to y, the size of x is greater or equal to y, and the size of x is equal to the size of y. Okay? So you can define these notions on the left-hand side using injection, surjection, and bijection. Now we can ask, well, what about strictly less than? So how can I define? You can tell me some ways. There are at least a couple of ways you could define strictly less than now with using these. Yeah.
That there exists an injection but not a surjection?
That there exists an injection but not a surjection. So in some sense, maybe this is what you're trying to get at, is like, you know, when you say x less than or equal to y, we're talking about like x, it's not the case that x is greater or equal to y, right? That's what it really means. And now if we know what this means, so we can say, well, it's not, there's no surjection from x to y, might be a good way, or equivalently that there's no injection from y to x, you can define it that way. Or maybe another way might be, you can say, well, it's the case that x is less than or equal to y, but it's not the case that the size of x is equal to size of y. Right? And so that you can write as there is an injection from x to y, but no bijection between x and y. Okay, so pretty intuitive stuff, hopefully. And yeah, so Cantor, basically his main contribution is to redefine in some sense for finite sets what does it mean to be two sets to be equal in size and one set to be greater in size, and say, you know what, these are actually the right definitions to use for infinite sets as well. Okay, so now let's talk about comparing infinite sets. And not much to say here other than the fact that, look, you just take the same definitions. Okay, these definitions work for infinite sets as well. Now I do want to make some remarks about this, some notes. First remark is, note that we're not defining what the size of x means here. I'm only attaching meaning to these expressions, x less than or equal to y, x greater or equal to y, x equal to y. I'm not attaching any meaning the size of x. So in 251, if you write size of x where x is an infinite set, this will not type check, right? We're not going to talk about that. So we're only defining for these expressions. Note two is that this is just one way to attach meaning to expressions like x, the size of x is equal to y for infinite sets. Okay, so I'm just saying, look, whenever I write the size of x is equal to size of y, all I'm saying is like there's a bijection between them. Okay, and that's the meaning I'm attaching to this concept. Okay, but at the same time, you know, this is just, you know, sort of like a philosophical position, perhaps you attach that meaning, but Cantor's statements, proofs, ideas, they're just statements about injections, surjections, bijections. If you, in particular, want to be like Galileo and say, look, you know, these notions for infinite sets don't make sense, I refuse to define them for infinite sets, fine, completely fine, you can take that position. All I'm saying is that whenever you see me write this, all I'm saying is it's a standing for like, there's a bijection. So every result, everything is really about injections, surjections, bijections, and that's it. Now, Cantor says, you know what, yeah, you should think about, you know, intuitively, you should give the meaning for a bijection as equal size set, and for the others as well. And I agree with him, actually, right? This does provide an intuitive understanding of these concepts. And yeah, it agrees with intuition in some sense nicely in many ways. And you should, I would argue that you should try to get comfortable with that equivalence in some sense, with this interpretation. That is a good interpretation to have. It will make things easier to think about and reason about. So in that sense, yes, but again, this is the point that I want to make. Good. Now let's do some sanity checks, because if we are attaching these meanings to less than or equal to and equal to compare sets, well, it better satisfy some properties that we would intuitively expect this notation to have. For example, we would expect that if the size of x is less than or equal to size of y, this is if and only if the size of y is greater or equal to size of x. If this is not satisfied, then this notation is not a good notation to use in some sense. It should be the case that the size of x is equal to size of y if and only if the size of x is less than or equal to size of y and the size of x is greater or equal to size of y. And similarly, x is less than or equal to y and y is less than or equal to z, x less than or equal to z should follow. And are these true? Yes, you can prove these. Using the notions of injections and surjections, these are provable without a problem. So good. So that's a good sanity check that this notation satisfies our expectations of how this notation should behave, and it does behave like that. Now let's talk about examples of bijections. Okay, and I'm sure, like, again, I'm going through these quickly. I will go through these quickly given, I'm assuming you have seen this stuff before, but please do, stop me if you don't understand something. So the first one is, let's talk about naturals and integers and ask, can we say that the size of the naturals is equal to the size of the integers? But all I mean by that is there a bijection between naturals and integers? And as you know, yes, there is a bijection, right? So we can list out the elements of the integers like this, 0, 1, minus 1, 2, minus 2, 3, minus 3, and so on. And then that gives us a nice now bijection with the naturals, right? So we can make a correspondence as you see here. Okay. Now, if you wanted to find, if you want to define an explicit formula, sure, you can do that as well. That's fine. This is a bijective function. Now you might be like, whoa, shouldn't, A strict subset of B imply that the size of A is strictly less than the size of B? This is kind of what Galileo observed. And, that's one maybe perspective to have. But at the same time, another perspective to have would be, well, what is a bijection? A bijection is just renaming of elements. And if you're renaming the elements of one set with the elements of the other set, renaming shouldn't change the size. So this is like going back to the conflict that Galileo observed. And he was like, whoa, what's going on? This doesn't make sense. He didn't decide to resolve this conflict, but Cantor did, and it was important that he did. Now, this example also shows a heuristic for showing that set A has equal size, is bijective to the natural numbers. The heuristic is to show that the set A is listable. So what do I mean by showing that A is listable? I mean the following process. If you can list the elements of A such that every element appears in the list eventually, then, then there's a bijection between the naturals and the set A, assuming A here is infinite. So why is that the case? Well, we did that with the integers. Well, the way I showed you how that, this was there's a bijection is that I listed the elements of the integers such that every element eventually appears in the list. And then that makes a correspondence between the naturals and the integers, right? So the nth element in the list maps to n in the naturals, right? So that's your sort of correspondence. The nth element in the list maps to n. So this is a heuristic. This is a nice heuristic that you can always use to show that there's a bijection with the naturals and the set you have in mind. You do have to be careful because here's another way to list, trying to list the integers like 0, 1, 2, 3, 4, 5, 6, and so on. This doesn't work because you'll never get to the negative numbers. So it is not the case in this kind of a listing that eventually every element appears in the list. So this listing doesn't work. But if you can find some way to list it where this works, then you're good to go. Okay, so let's see other examples. The squares, we've seen this already. This is Galileo's example. Is there a bijection? Yeah, well, I kind of listed the squares for you, 0, 1, 4, 9, 16, and so on. So every square will appear eventually in this list. So this set is listable, meaning it has a bijection to naturals. Explicit formula, if you want. This is the formula for a bijective function f. How about the p being the prime numbers? Okay, so we have the prime numbers p. And yeah, I kind of listed it out for you, right? So listable, 2, 3, 5, 7, 11. Eventually, every prime number will appear in this list. So that shows the sort of bijection. Now, if you want a formula, what's the function? Well, the function is f of n equals the nth prime number. It is, and the reason I bring this up is because, don't think that you need an explicit formula to define a bijection between two sets. In many cases, an explicit formula won't exist, actually. This is a perfectly fine way to define a function, define a bijection. Okay, formula sometimes just doesn't exist, but that's okay. How about z times z? Okay, so tuples where the coordinates come from integers. So let me draw this out for you. Okay, so we have all these points corresponding to the elements of z times z, 0, 0 in the middle. So how can we show, or is it true that this is actually equal in size to naturals? And how can I do that? Well, we can sort of use the listability heuristic, right? So how can I list it? How can I list elements?
You could like start from the center and then like rotate around like each square getting like larger and larger.
Nice. So you start at the center and you're rotating around, creating sort of like a spiral shape, right? And why did you decide to do it that way?
Because like by definition, you know, like every single file will eventually be covered.
Right, so you're saying this way I make sure that every element of z times z eventually gets covered, right? And that's important. Yes, you're absolutely right. You got it spot on. Right, so if you do this kind of a spiral shape listing, then you will eventually get all of the elements. If you were to do it like, oh, I'm going to start in the middle, I'm going to go one step to the right, and then another step to the right, another step to the right, another step to the right, and so on, and try to list in that manner, it won't work, right? Because you will be stuck at that row. You'll never make it to the next row or the row below it. So then it's not, in that sense, listable. I mean, you don't demonstrate that it's listable in that fashion. To demonstrate it's listable, you have to do this, you can do this kind of a spiral shape to make sure that every element eventually appears in your list. How about our good old friend 0, 1 star? So this is, let me remind you, the set of all finite length binary strings. So is there a bijection here with the naturals? How can I see that? Anyone? Yeah. The length of the binary string, right? So very good. So again, use the listability heuristic. How am I going to list it? Well, list by length, right? So you can say start with the empty string, then list the strings of length 1, list the strings of length 2, list the strings of length 3, and so on, right? For every length n, there are finitely many strings of length n, right? So this is, you can go by length and then list all the strings of that length. And this will, so then eventually every obviously string will appear in this list. And how about sigma star, where sigma is bigger? Let's say sigma has like 251 symbols.
It's the same thing. You just list them out by length, except that the strata will have size 1, 251, 51.
Yeah, exactly. Same idea works, right? As you're pointing out, of course, listable. Length 0 string, length 1 strings, length 2 strings, length 3 strings, just list them out. All of these are finite in size. Length 3 strings are finitely many. For any length n, they're finitely many. Okay? Okay, so the picture so far is this. Okay, so we have finite sets. That's fine. Then we have all these other sets like naturals, integers, z times z, sigma star, primes, squares, and they're like all in bijection with each other. And of course, we want to know, like, well, does that cover everything, or might there be something outside here? But before we get to that question, how should we define, like, one important thing is, it seems like it would be nice to define the set here. How should we define the set? Okay, and there are actually two very good definitions, two reasonable definitions, one being better than the other one. The first definition, which is kind of like, what you would see in the standard textbooks, I guess, is that, these are sets. This set contains all those sets S, such that the size of S is less than or equal to the size of N. There's an injection from S to the naturals. Now, what that points out, or heuristically what that means intuitively, is that your set S is in some sense, again, it's listable. You can also think of it as an orderable set or a countable set. And in fact, the set, as you know, right, is called countable sets. Okay, and it's kind of coming from this kind of heuristic that, the size of S, there's an injection from S to the naturals. But now notice that the choice of the N here, it's a bit arbitrary, right? I mean, size of N is equal to size of Z, Z times Z. I mean, I could have picked Z here as well. I could have placed Z here. It would be the same definition. I could have picked primes. It would be the same definition. It doesn't change the definition. The choice of naturals is kind of arbitrary. And so you could, for example, pick sigma star and say sets S such that the size of S is less than or equal to the size of sigma star. And now what does that mean? It means there's an injection from S to sigma star. And what does that mean? We've seen this week 1.
It's encodable.
Encodable sets. If you remember from week 1, we defined the notion of encodable sets. And this is precisely that definition, right? There's an injection from S to sigma star. And my claim would be that the second definition actually is a better definition. It's a more intuitive definition. It captures the essence of countable sets, I would say, much better than the first definition does. And yeah, and then to illustrate that point, actually, let's do some examples. First, let's talk about rational numbers. Is the rational numbers countable or not? Now, you know, we can draw like a number line. And, you know, we can try to use the first heuristic, like the original definition of countability, that kind of basically the listability definition, and ask, can we list them? Can we list the rationals in the order they appear on the line? Right? Maybe I start at 0 and then go left and right small values and then try to like list it that way. Would that work? And why doesn't it work?
You can find an arbitrarily small rational number in either direction.
Yeah, you can find arbitrarily small rational number in every direction. Basically, the way we say this in mathematics is that rationals are dense in the reals. For any interval you pick, for any two real numbers that you pick, there's always a rational number between them. It doesn't matter how narrow you pick that range, there's always a rational number between those two values. So this is what we mean by rational numbers are dense. So if they're dense, you're never going to make any dent in the listing. You're never going to go anywhere. So this doesn't work. And then you can think about, oh, can I list it, you know, more carefully? And yes, there's a way to list it. Maybe that's the way they show you, like, you know, oh, if you do this like table and you go on the diagonal and you can list it out. Okay, fine. But let's think about the encodability definition. If I said, you know, is this set of rational numbers encodable? You could say, of course. I mean, this is the way we, you know, communicate rational numbers to each other. How do we communicate a rational number? You know, the alphabet that we'll use is the digits, division sign, and minus, let's say. And every rational number can be described by a finite length string over this alphabet, right? So something like minus 210 over 251, let's say, right? And that's it, right? So you say, look, Q is encodable, therefore it's countable, done, right? Nothing more to it. It's very intuitive. You immediately see, right? Yes, of course. I can write down every rational number as a finite length string. Every rational number as a finite description. I'm done. Here's a more sophisticated one. Let's say the set of all polynomials with coefficients coming from Q, right? The set of polynomials with rational coefficients. Well, you know, is an example of a set of a polynomial with rational coefficients. Now you can go and, you know, think about, okay, can I list it out so that every element appears in the list? You can try to think about that, but that's the wrong way to think about it. Like you ask, can I represent it as a finite length string? Yeah, I mean, I just did. Every polynomial has a finite length string representation, okay? The way we communicate these objects with each other, you know, that's the way it goes. Every polynomial can be described by a finite length string over this sigma. You have the digits, x plus minus multiplication, division, exponentiation. And here's your string representation for that, for example. So you immediately see, like intuitively, if you use the second definition, it's immediately clear. And I would even say, like when you talk about, let's say, well, is there something outside of countable sets? Let's say the real numbers. And then you might say, okay, intuitively, before I write a proof, can I like judge whether the real numbers should be countable or not countable, actually? Now you can use the first definition of countability and listability definition and say, well, maybe there is a way to list them out in a smart way, like with the rationals. Rationals were dense in the reals. And there is actually a smart way to like list out the rationals. Maybe there's a smart way to list out reals. It's not clear. But if I said, hey, use the encodability definition, you know, is there a finite length string representation of arbitrary real numbers? Then it's almost by definition, like you see that, oh, of course not, right? So real number is like, you know, you have infinitely many decimal points. You might have pi with its infinitely many decimal points, right? You sort of almost like immediately you see, no, this cannot be a countable set because it's not encodable. Another set that you'll see in the textbook, this is our notation for the set of all infinite length binary strings. Okay, the set of all infinite length binary strings. And this again, like if you ask, okay, the set of all infinite length binary strings, is that countable? It's almost by definition, it's not countable if you use encodability, right? I mean, you still need to make an argument there because you need to argue that you cannot somehow compress these infinite length strings to finite length strings. Sure, there's a neither argument, but intuitively, it immediately gives you the right picture. Okay, so this will be our now task to figure out, well, is there something outside of countable sets? Okay, but one exercise I'll give you, some interesting thing. You might ask, like, is there some notion, is there some infinity that is beyond finite sets, right? You go beyond finite sets, but you're not exactly in bijection with the naturals. And it turns out that the answer is no. So if you're a countable set, then you're either a finite set or you have a bijection to naturals. It's a little exercise for you. I mean, I'm sure you've seen this, but yeah. Okay. Good. So now this brings us now to great idea number 2, diagonalization method. And as I said, this is, I think, one of the top 5 proof techniques in all of mathematics. Extremely, extremely powerful.